Hi! Within this lecture, I'm going to solve that Fibonacci sequence problem with recursion and also with iteration as well, with creating a loop as well. Because we have been talking about this, we always say that, yeah, there should be many solutions, but in fact, you have to see them in order to compare them and in order to use them whenever they are necessary. Right? So that's what we're going to do. And in fact, it doesn't make many difference in terms of time complexity in many cases, but sometimes writing it with a recursion should be very easy, or sometimes it's a necessity as well. So I'm going to start with the recursive one, and I'm going to call this something like, I don't know, recursive Fibonacci, whatever you may want to call it. Okay, so I'm just gonna call it recursive Fibonacci, and here you go. Now, obviously, we're gonna take an n or number as an input, so it will actually state that where we should stop like this. Okay, so this is what we are trying to create. If f is 0, then we're gonna return 0. F is 1, we're gonna return 1. And in fact, that is the exit condition, right? So this is actually the solution. We are literally given the solution inside of the problem. So if n is 0 or n is 1, then we're just going to return those numbers, right? But else, we're just going to recursively call the Fibonacci and just sum up the two preceding values, like this. If you read the question, that is exactly what it's written over there, right? In a form of pseudocode. Obviously, we have to return this. But that's it. That's the solution. So if you call the recursive Fibonacci, for example, with 10, then we're just going to get 55, like this. So if you just count this, you will see that obviously you need to include 0 as well. And we're just going to have that number. And here you go, 34. It works. If you give 8, we're going to get 21. If you give 7, we're going to get 13. If you give 6, we're going to get 8. Like this, it works. So far, so good. Now, this is the recursive solution. And as I said before, it is actually given in the problem. So all you have to do is just read it out and just code it like this. It's great. But again, this is not the only solution. What we can do this iteratively, which means that we can create a loop to iterate over the array or iterate over the range or something like that to figure out the summation of those numbers. So we can do that with two-pointer approach. And again, I'm not doing that in order to say that recursion is better or worse. So there might be some cases where you should use recursion. There might be some cases where you should iteration. If you know them both, then it's going to be okay for you. And again, it works. It works. The recursion works in this case. As long as you don't forget about the edge cases or exit conditions, then you're gonna be fine. Okay? If you forget about them, then you're gonna stuck in an infinite loop, which is not what you want. And in this case, it's very obvious. If n is 0, we're gonna return 0. If n is 1, we're gonna return 1. But if not, then we're just gonna sum up the two preceding values, right? So that's the definition. So let's try to do this with iteration. As I said before, it's very easy to do so. We only need two variables, like two pointers. We can start with 0 and 1 and just sum them up together by incrementing them, or just summing up them and assigning the new values to them. So let me show you what I mean. Obviously, we're going to start with 0, right? So that's the official definition. I've skipped that because it doesn't actually affect the outcome of the summation, but you have to start with 0 and just add them together until you reach what number you are trying to reach, right? So if you look at that, we can just do that with two pointers, two variables. Let me show you what I mean. I'm just going to call this iterative Fibonacci, and we're just gonna have like a standard x and y operators, x and y variables. We can just make like x0, y1, okay, and we can do that like tuple unpacking way, like in order to show that we really know Python to do interviewer, okay. So x is 0, y is 1 in this case, and what I can do, I can try to create a for loop in a given range like this. So the range should be n, it will just go up to the n, okay, and for every I in that range, for every step in that range, I'm going to sum x and y and make it equal to the new y like this, and x will be new y. Okay, but obviously this won't work because we are changing the value of x. So what I can do, I can just make it equal to a temporary variable like this, temp, and then when I change the value of x, now I can just add temp to the y. But obviously we know how to handle that. We can just do that with tuple unpacking. So if you see this, x will be y because we're just skipping one right for the x, and y would be x plus y, and we're just going to return the x at the end of this. So let me show you if this works or not. I'm just going to say iterative Fibonacci, and if I give 6, for example, we're just going to get 8. So 1, 2, 3, 4, 5, 6. Here we go. We're getting 8. Now we can try that with any other number as well, but we are doing this as it should be, right? Because in the range of 6, it's just going, let me just do this with a list, it's just going 6 times, we know that. And for 6 times, it's just skipping x to be y and trying to sum x and y together and just make it equal to the y. At the end of this range, x will be the value that we are looking for, and y will be the value just right next to it. And we're just going to return the x. Obviously, we can try to change the variable names like first pointer, second pointer, something like that. And obviously, you can try to play with this in the Jupyter notebook, print this out to just follow up the steps, but I believe this is pretty self-explanatory. So it should be easy for you to do that in the iterative way as well. But in my opinion, solving this problem with recursion is much more explicit. Okay, it just makes much more sense to me doing it like this rather than this. But in a way of technical speaking, it doesn't really matter, right? We're just doing the same thing in here and over there as well. But there might be some kind of difference when it comes to something called memoization. So in order to understand that better, we're just going to have a separate lecture because we need to understand the concepts of dynamic programming as well for the upcoming sections, and it would be very good for us. So that is why we're just going to spend a little bit more time in here for in order to understand everything comprehensively. So I'm just going to stop here and continue within the next lecture.